Today, in this explainer, we are absolutely mastering the gear position sensor. And my goal, turning you into a total diagnostic sniper. We're going to walk step by step through the exact diagnostic process I use every day as a professional mechanic. By the time we wrap this up, you'll know exactly how to test, confirm, and perfectly calibrate these critical components, all without ever blindly firing the parts cannon. So grab your notebook and let's get into it. Okay, let's start right off the bat with a really severe customer complaint. You see a ticket that says vehicle creeps or lunges when placed in park. Look, when a car lunges in park, we aren't just fixing some annoying little glitch. We are literally preventing a catastrophe. I really need to emphasize this in your mind right now. The grave safety risks of driving with an unstable gear signal just cannot be overstated. When a vehicle creeps after being put in what looks like park, you've got a terrifying situation where unintended gear engagement creates huge parking risks. See, the transmission control module, or TCM, it commands hydraulic pressure purely based on what this sensor tells it. So if the sensor screams drive when the driver selects park, someone could get seriously hurt. Here is our diagnostic plan of attack for the day. We're hitting the complaint, sensor anatomy, the digital scan, physical tests, and finally, the fix. Starting with Section 1, the complaint, we're looking at the symptoms and the stakes. Now, you have to understand that these symptoms usually progress in stages. It doesn't all happen at once. It might start with just a flickering PRNDL display on the dash or a tiny slight hesitation on startup. But then sensor drift kicks in, and that causes a rough idle and really poor engine load calculations. Why does that happen? Well, the engine control module actually applies completely incorrect load parameters because it thinks the car is sitting nicely in neutral, but it's actually pulling in drive. Eventually, you're going to hit limp mode, which forces the transmission to lock into second or third gear just to prevent internal damage. And at the absolute most advanced failure stages, you see that unintended gear engagement we talked about, or even a total loss of drive where the transmission acts like it's in a permanent fail-safe neutral. Oh, and hey, if that happens and you just need to get the dead vehicle rolled into the bay, you'll need to know how to safely bypass the starter relay interlocks, but remember, that is strictly for shop movement only. Moving right along to Section 2, Sensor Anatomy. Let's look at what we're actually testing. Notice the incredibly stark contrast here between older resistive wiping contacts and the highly precise modern non-contact sensors. The old-school contact resistive units, they output a variable voltage based on a physical sliding wiper inside. And guess what? Over 100,000 miles, those physical contacts just flat out wear out. Modern Hall effect and optical sensors, on the other hand, are a whole different ballgame. They use magnetic fields or light to output a super precise digital pulse width modulated signal. And the best part is, there's zero physical wear. So when you're diagnosing, you're looking for clean, smooth, resistant sweeps on the old units and absolutely perfect, crisp digital square waves on the new ones. Remember, modern vehicles are basically rolling computer networks. A failing gear position sensor will actually corrupt the shared CAN bus data stream, and that triggers a massive cascading wave of ABS and stability control faults that will absolutely confuse a rookie mechanic. If you see the traction control completely disabling itself alongside a shifting issue, you need to interpret that CAN bus signal data very carefully. It is so often not a bad ABS module, it's just a corrupted gear position signal confusing the stability logic, because, well, the computer needs precise gear confirmation to manage torque control. Keep in mind, these sensors live in a totally brutal environment. They endure 120 degrees Celsius heat cycles just under normal transmission operation. This extreme temperature cycling heavily impacts long-term sensor connector reliability. The repeated thermal expansion and contraction over the years literally cracks the internal solder joints and warps the plastic housings, which is exactly what allows moisture to sneak in there. All right, Section 3, the digital interrogation. Let's plug in. So here is your step-by-step workflow for verifying live scan tool PIDs. First up, you always include a systematic check for diagnostic trouble codes. Pull those P0705 through P0709 codes to confidently confirm the sensor circuit is your prime suspect. Next, pull up and monitor your live data streams. You want to slowly, intentionally cycle the shifter through park, reverse, neutral, drive, and your manual gears. The signal value on your screen should change smoothly. If you see erratic values, stuck signals, or let's say it flickers to neutral when your hand is physically holding the shifter in drive, boom, you've just visually confirmed the fault right there on your screen. And this right here brilliantly illustrates exactly why we use lab scopes on modern vehicles. By analyzing the live signal waveforms for Hall effect sensors, we can detect these tiny, almost invisible internal timing deviations. We're talking about a 200 millisecond signal dropout. That tiny blink of an eye can cause starting hesitation or force the TCM to instantly lock the transmission into fail-safe limp mode. The computer is just so incredibly fast that if it loses sight of the gear for even a fraction of a second, it totally panics and goes into self-preservation mode to protect the transmission.
Okay, Section 4, the physical exam. Time to get our hands dirty.
You are going to need to verify these exact values by comparing your observed resistance values against the specific manufacturer's service manual chart for whatever car is in your bay. For instance, on a 5-volt reference system on an older contact-type sensor, you might be looking for a perfectly clean 0 ohms in park and maybe 2.4 kiloohms in drive. But the golden rule is, if your readings don't perfectly match the OEM chart, that sensor is toast. In this shop, we don't guess, we test. So grab your multimeter right now to verify the voltage ranges for each gear position. With the key on and the engine off, you're going to carefully back probe the signal wire. You want to see that 0.5 volts in park scaling up smoothly to around 4.5 volts in drive, depending on the exact system, of course. After that, unplug the sensor completely and check the resistance across the pins. Now, what if the voltage checks out perfectly, but the customer still has an intermittent signal loss? Well, you need to isolate those intermittent circuit faults using a wiggle test on the wiring. Literally get your hands in there and aggressively wiggle the harness while you're watching your live data or your multimeter. I guarantee this will expose hidden corrosion, degraded weather seals, or spread terminal pins that only break connection when the engine vibrates out on the road. So, a really crucial skill here is knowing how to differentiate an internal sensor failure from an external transmission linkage misalignment. Check this out. If you measure infinite resistance, which shows up as OL on your meter across all positions, the sensor is internally destroyed. It's done. But if the voltage is just slightly out of the expected range, let's say you're getting 0.7 volts instead of 0.5 volts in park, you most likely have a bent or worn shift linkage. Literally, even 1 or 2 millimeters of physical misalignment throws the electrical reading completely out of whack. You've also always got to check for physical issues like fluid leaks or damaged wiring harnesses. You need to know how to identify transmission fluid contamination because it causes wild false signal readings. Automatic transmission fluid, or ATF, can actually leak past failed internal seals and go right into the sensor housing. And since that fluid acts as a conductor, it ends up bridging the electrical contacts and creating completely erratic, totally false gear readings. Almost done. Section 5, replacement and calibration. Let's fix it right. Let me clarify right now when to choose OEM parts versus aftermarket options because it depends entirely on the sensor type. For precise, modern Hall effect sensors, OEM is absolutely mandatory, no debate. The calibration tolerances are just way too tight for cheap aftermarket knockoffs. However, for the older resistive contact type sensors, an aftermarket unit is generally acceptable, but only provided you verify that its resistance values strictly match the OEM service manual before you even think about installing it. All right, let's detail the exact steps for sensor alignment and post-replacement calibration routines. First, you have to physically align the new sensor body perfectly to the OEM reference marks on the transmission case, making sure the selector is in neutral. Then torque those bolts to spec. It's usually a pretty light 7 to 12 Newton meters. Finally, and this is the step guys skip, you must execute a neutral position learn procedure using your scan tool. If you skip this electronic relearn, I promise you your shift quality issues and your fault codes will come right back on the test drive. As a final step in our bay checks, go ahead and clear all those old codes and take the car for a test drive while actively monitoring your live data. Also, let's detail when you actually need to replace the transmission fluid during a sensor repair. If you found that the ATF was heavily degraded, or if you found that fluid contamination inside the old sensor housing causing a short, you absolutely must perform a full fluid service right now. Otherwise, that nasty, dirty fluid is just going to destroy your brand new sensor all over again. So keep your multimeter handy, always trust your live data, and remember that truly mastering diagnostics means respecting how one tiny component can bring a massive, complex machine to its knees. As you roll your toolbox shut today, I want you to think about the size of the sensor and ask yourself, how much power does a single microchip hold over a 2-ton vehicle? Pretty crazy to think about, right? Keep up the good work out there.